Yesterday we introduced the idea of acceleration. Okay, we had talked about constant velocity before that. Constant velocity meaning that an object is traveling at the same speed or the same velocity the whole time. It's not speeding up. It's not slowing down. Again, yesterday we introduced this idea of the object is speeding up or slowing down. Acceleration. We said we had two groups of problems now. The first group of problems we'll call Group A. Those problems involved constant velocity. And in those problems, we always use the equation v equals delta d over delta t. Sometimes with the arrow over it, sometimes without the arrow over it. It all depends upon whether we're talking about speed or velocity. But this is our Group A equation. Every time an object is not speeding up or slowing down, we will use this equation. There's no other option. We have to. But when we have a problem involving acceleration, when we have an object speeding up or slowing down, whether it mentions the word acceleration or not, we will make it a Group B problem. Our Group B problems are a little bit more complicated because we have 5 equations that are valid for those problems. We have to identify that it's Group B, write down our givens, and then look at which givens fit which equation the best. Okay? And that's not overly hard once we get the hang of it, but in the beginning it's a little bit tricky because we're not used to doing that. Okay, we're used to going straight to the equation that we know is going to work. Okay, we can't do that so easily now. What are those equations? Well, the first one in our Group B list is the most obvious. That's essentially the definition of acceleration, the rate of change of velocity. Not the change in velocity, but rather the rate, how quickly the velocity is changing. Okay, we don't care so much about what the change in speed or the change in velocity is. An airplane changes velocity from 0 to 800 kilometers per hour. We don't care about that. We care about what the rate of acceleration is, how quickly it's changing its velocity from 0 to 800 kilometers per hour. Another equation within our Group B equations is delta D is equal to VI delta T plus 1/2 A times delta T squared. What did VI stand for there? Yep. Good. It's the initial velocity. A stands for the acceleration in meters per second squared, right? Then we had another equation within Group B that looks almost the same as this, but there's two small but important differences. It goes like this. VFT minus 1/2 AT squared. So same structure, but we've got a VF instead of a VI, a final velocity, instead of an initial, and we've got a minus sign instead of a plus. We also had D is equal to VI plus VF over 2 times T. And this is kind of a bit of a different one because this one doesn't even have acceleration in there. We're talking about an acceleration problem. Object speeding up, slowing down, but you don't even see an A in there. That's okay. It's still valid in exactly the same situation as the other ones are. If it involves acceleration, if the speed is changing, then this equation is valid. Now, it doesn't mean it's going to work for you. You might not have the givens that match up with that, but you're allowed to take a look at it at least. And finally, we had that last equation, VF squared is equal to VI squared plus 2AD. What did delta D stand for? Tell me what delta D stands for there, please. Josh? Sorry. Displacement, yes, sorry. Displacement, good. What does VI stand for? Yep. The initial speed, good. Not initial velocity, initial speed, good. And VF, of course, stands for the final speed, right? Make sense? So let's draw a line down the middle between those, and let's look at every single time we have a problem, let's look at whether it's a Group A problem or a Group B problem. If it's Group A, go straight here and use this equation. Don't do anything else. If it's a Group B problem, go straight to this list, write down your givens, and then figure out which equation fits those givens the best. We talked about this a little bit yesterday, right? Fraser, I think, brought it up. Sometimes we look at an equation that seems to fit the givens, and great, we get the right answer. But sometimes there's another option as well, or maybe even 2 or 3 other options as well. Maybe you use one of the equations to solve for something else that you weren't looking for, and then use that value to use another equation to solve for what you are looking for. So there's not one right way to do a lot of these questions. There's usually a quickest way and a shortest way to do them, but there's often 2 or 3 correct ways to do them. And I don't care which way you do it, as long as it's the correct way. I don't care if it's the quickest way. Okay? I care if it's the correct way. All right? We did 2 example problems with this stuff yesterday, and then we did practice problems that go along with them. We ended off with these practice problems on page 48. Are there any issues with these practice problems on page 48, please? Should we go over question number 2? Yes? No? All right. In the absence of anybody saying anything, we will go over question number 2 here. It says a ball moves up a hill with an initial velocity of 3 meters per second. That's going to be VI, right? Let's write down VI is 3.0 meters per second. 4 seconds later, that's going to be our time. 4 seconds later, it's moving down the hill at 9 meters per second. What is this 9 meters per second thing? If VI is 3, T is 4, what's 9? We all know this, right? What is it? Oh, good, good. It's negative 9 meters per second. Why did you say it's negative? It's not what I was looking for there, but you're absolutely right. Why did you say it's negative? Good. It's going in the opposite direction. Now, it doesn't matter whether we define up the hill as positive or down the hill as positive, but one of them has to be positive. If we define up as positive, then VI will be positive 3. If we define up as positive, then VF will be negative 9 because it's going down the hill. And we want to find the displacement there. Which of these, is this group A or group B? Constant velocity or acceleration? Yep. It's acceleration. So it's a group B problem, right? Those 5 equations that we have right over here in our group B column are the ones that are valid. They're all valid. If you try one of them, you will not get the wrong answer, assuming you do everything correctly within that. Even if it's not the one that will get you the correct answer, you will not get the wrong answer. Okay, the worst case scenario is you plug some numbers into here, you end up with 2 or 3 unknowns, and you don't have anything. Okay, so then try another equation. Let's try to find the equation that works best first, but if we can't, then just try one. Pick one. Go with it. If it gets you an answer, great. If it doesn't, then try another one. I can promise you, as long as you do it correctly, it's not going to get you a wrong answer. None of these are. Rutgers, you have a question? Your hand was up. No? Which one do you want to try here, guys? We got VI, we got VF, we got T, we're looking for D. Which one do you want to try here? We'll call this one 1, 2, 3, 4, or 5. Which one seems to fit the best, Rutger? We've got VI, we've got VF, we've got T, and we're looking for D. Yeah, I think we go with number 4 as well. Okay. But if you didn't spot that, okay, if you had a little bit of trouble finding that we're going to go with number 4, try number 1. Okay, what's the worst that can happen? You don't get an answer. Okay, big deal. You're not going to get the wrong answer. You're just not going to get an answer. Let's try number 4 here, okay? Let's say D is equal to VI plus VF over 2 times T. Okay, VI is 3. Don't forget to add negative 9 as opposed to positive 9. Divide that by 2. We do the math on that, it should work out to be negative 12 meters, which means it's 12 meters. Since we defined up as positive, this would be 12 meters down the hill. Is that good? All right. Let's try another one. Lots of examples on this stuff because it's a pretty important topic here. So there's a golf ball that's initially traveling at 25 meters per second, hits a sand trap, and slows down with a rate of acceleration of 20 meters per second squared. What's its displacement after 2 seconds of slowing down? 25 meters per second is something. Something is negative 20 meters per second squared. Something is 2.0 seconds. Tell me what that 25 is. Is that a VI? Is that an acceleration? Is that a VF? Is that a delta V? What's the 25 meters per second here, please? Good. We're going to call it VI. It's initial velocity. Good. Tell me what that negative 20 meters per second squared is. There's your little hint right there. Meters per second squared. That's going to be good. It's acceleration. And the fact that it's a negative acceleration just means that it's slowing down. Okay? Positive acceleration would mean speeding up, negative slowing down. 2 seconds is going to be the time, right? We're looking for the displacement, so we're looking for delta D. By the way, I forgot to ask you this question. Is it group A or is it group B? I think it's pretty clear that it's group B, right? We've got the value of the acceleration. Pretty clearly, it's accelerating. Slowing down, but still accelerating. Okay, which one seems to fit the best? We've got VI, we've got A, we've got T, and we're looking for D. Which of our group B equations seems to fit the best? We've got VI, we've got A, we've got T, we're looking for D. Josh? Let's try number 2. Okay, if you didn't spot that, that's okay. Try number 4, try number 1, try number 5, doesn't matter. Okay, number 2 is going to work the best for us. But if we try number 5, we're not going to get the wrong answer. We just know we're going to have to try again. 2 says D is equal to VIT plus 1/2 AT squared. We got 25 meters per second times a time of 2.0 seconds. Now you got to be really, really careful here with this one. 25 times 2 is 50. Let's do it in steps here. 25 times 2 is 50. 2 squared is 4, times 20 is 80, times 1/2 is 40. What's wrong with this? I've made a mistake in here on purpose. I want you to tell me where my mistake is. Yep. Yes, it should be a negative 40. How come? Yeah. 1/2 times neg 20 times 2 squared is neg 40. So it becomes 50 plus negative 40, which makes it not 90 meters, but rather 10 meters. How many digits should my final answer be? How many digits? It should be 2 digits, right? 2 digits, 2 digits, 2 digits. Final answer should be 2 digits. That's a third of the 5 acceleration equations that we've used now. Okay, be prepared to use all 5 of them, okay, whichever one seems to fit the best. All right, let's see what we can do with this one. All right, everyone, you've had a chance to work on these. Let's take a look at number 2 together here now. It says, a motorcycle traveling at 110 kilometers per hour on a flat road applies the brakes at 0.80 meters per second squared for 1 minute. How far did the motorcycle travel during this time? Is this group A or group B? It's group B, right? All of the problems that we've been doing lately have been group B problems, but we still want to ask yourself that question. Right? 3 weeks from now, maybe you have a test, and you've got 7 questions. Okay, you've got to sit down and identify each of them as group A or group B, because some of them might be group A and some of them might be group B. So let's do that still every time, even though we kind of expect them to be group B at this point. Okay, this is a group B problem. Involves acceleration. Let's write down our givens. Okay, what is this 100 kilometers per hour thing? It's a velocity, right? But is it V? Is it VI? Is it VF? Is it delta V? What is this velocity that we call 100 kilometers per hour here? It's VI. Good. It's the initial velocity. Now, we also know that we're going to want to convert that to meters per second. Let's not forget to do that. It's probably not a bad idea, actually, to Just circle that in red to remind us that we have to convert that to meters per second before we actually solve anything. I see something as 0.80 meters per second squared, and I see something as 1.0 minutes. Tell me what the 0.80 meters per second squared is. Yep. Good. That's the acceleration, and this one's going to be the time, right? Now, a couple little things here. That time in minutes, we probably don't want to be in minutes here. When you're doing v equals d over t, the standard units are meters and seconds, although you can really use whatever you want. When we're using acceleration, we've got to be in meters and we've got to be in seconds. So this time of 1 minute, we want to convert that to seconds. We'll deal with that in just a moment. There is one more thing that I've got to be really careful of here. If you're not careful of it, and it's a tricky little thing here. If you're not careful of it, you'll get the wrong answer. What is it, Josh? This has got to be negative 0.80. Why? How come it's negative, Fraser? Good. It's slowing down. It's decelerating. Okay, how many people caught that? How many people caught that it should have been a negative value? Good. Good. That's a tricky thing to spot at this point in the year. Okay, very good if you did catch that. You're going to see in a minute once we use our equation, it's going to make a big difference in our answer. We'll make it positive or negative. All right, let's convert this to meters per second. 100 kilometers is 100,000 meters. 1 hour is 3,600 seconds. That gives us a speed, I believe, or a velocity, I believe, of 27.7778 meters per second. 1.0 minutes, if we multiply that by 60 to get seconds, of course, we're going to have 60 seconds here. Now, somebody made the very good point. I thought it was a very good observation that all of these equations have displacement in them, not distance. And we're looking for the distance, right? How far did it go? Not looking for the direction. Here's the thing. It hasn't changed direction, right? It's going in the same direction. If it hasn't changed direction, what do we know about the value of distance and displacement? Somebody said it? They're the same. They're not going to change. So if we can find displacement, then we've got the distance, right? It's the same number for distance. So let's do that now. The displacement is going to be equal to VIT plus 1/2 AT squared. VI is 27.77778 times the time of 60 seconds. We add to that 1/2 of negative 0.80. Again, we've got to be careful with that negative, just like we did in our example problem, times 60 squared. Let's get a number for that. When I do that, I end up getting 226.7 meters. Where do we round that to? How many digits should that be if we look back to our original data? It's going to be 2, right? This is 3 digits right here. This is 2. This is 2. Final answer should be the least precise of all our pieces of data, so it's going to be 2. The only way we can do that as 2 digits is to say 2.3 times 10 to the 2 to put it in scientific notation. Okay, if we say 230, rounded to 230, that's not 2 digits. That's 3 digits. So don't really have a choice. Got to go in scientific notation here. Rutger? Don't. Okay, that's why you should not round off your initial velocity. Okay, it's a good point, Rutger. I'm glad you mentioned that. 1 second here, guys. Hold on, please. Until you get to a final answer, don't round. I mean, in the end, for practical purposes, you're going to have to round somewhere, right? We get that 100 kilometers per hour converted to meters per second. We can't go 27.777 to an infinite number of digits, but we can go to 4 or 5. If it's not a final answer, Rutger, don't round it until you get to at least 4 or 5 decimal places. Does that make sense? If you do, then it leaves you open to the possibility of getting a wrong answer. Slightly wrong, but still wrong. Okay? Okay, have a good weekend, everyone.